Hello and welcome to the next Learn Calculus and More video. Today we are going to be focusing on a brand new topic called integration. This is the starting point, fair warning, of our Level 2 series of videos for calculus. We will still be running the Level 1 series at the same upload rate as this one. I'm sorry for the lack of videos over the last couple days, but I've had my own exams and job that I've had to work with here, so I'm making them every single chance I get because I love doing it. The physics, calculus level 2, and calculus level 1 will all be running. Physics is more of those love child where I'll get to it when I have time, but primarily it's going to be this calculus stuff. So if I have some spare time over my hand, which I should because we're getting towards the winter break now, where I will be able to make lots and lots of videos and have lots and lots of fun with you guys, be able to explain all sorts of things, answer any questions, and I can't wait. And I can't wait for the next coming semester as well, because we'll even be able maybe to get into some electricity and some magnetism, or maybe even some thermodynamics and stuff like that. But for right now, we've got integration. This will be in a separate playlist from our Calc 1 sections in our physics section. So this will be in a separate one. If you don't want to get involved with this, you do not in any way need to feel obligated to watch these if you are not at this level yet, because we're going to be under the assumption that you've done everything up to this point, like Riemann sums, derivatives. You understand what areas on graphs are, what distance on graphs are, just those kinds of things. Implicit differentiation, what differential forms are. So in this one, we're going to really get stuck in. This is actually the first part of a two-parter for the introduction to integration because it's such a difficult topic that we actually need to separate it up, or I need to separate it up in order to explain it effectively without um, plummeting the quality of the explanation by trying to do it computationally and conceptually. So it's easier to do it visually, conceptually, and notation wise in its own thing, and then cover the formula and how it works in its own separate video, which I will be putting up pretty soon after this one. So let's get into this. So first off, we're going to do this with notation. So our notation, if I had asked you over your career in calculus so far, if I said, hey, take the derivative take the derivative of f of x equals x squared plus 14. You'd probably look at me and say, all right, well, that's super easy. It's just 2x because the power rule, this cancels and this multiplies down to here. And then we decrease our exponent by 1. So then we just get the 2x. Now, this is great that you know how to do that, that you know that that's f prime of x of that function. But what if I said go backwards? Go backwards. So let's say if I gave you f of x equals 12x plus 5. Would you be able to go backwards? Because the other term that's frequently used for integration is antiderivative. Because it's quite honestly the same thing. It's using integration and derivatives, you can get from this point and this point indefinitely by just doing them over and over to each other, and maybe even go a step backwards or things like that. And you can find a lot of different things with this. But let's get into actually how to write this, because we know that the differential form for a derivative is dy dx, and that we can write that as f prime of x or g prime of x or y prime. We could just go on and on and on and on and on with all these different ways that we could write the same exact thing. I'm gonna make the side note real quick. The way you write your D, the letter D, becomes very important from here on out. Because if you write your letter D like that, or like that maybe, or even like this with a weird backwards 6, I hope you don't do that because that's just weird. I don't know what's going on with you. But if you write it like either of these two things, you need to work on not doing that anymore because that with integration entails something else completely, or with derivations even, because it's actually what's called a partial. It's called a partial derivative. So we would actually have the partial of x over, not an x there, over, uh, over the partial of t. So that's just basically saying the partial derivative of x. Now, that is something that's at a pretty higher level, generally in level 3 courses, but we don't really need to worry about it right now. Just work on writing your x. You could work on writing the d. You can write it like that. You could do a stick and then the curve, or you can even do it like uh, uh, you could even do it like that if you wanted to. Just something where it's very clearly a a regular print looking d. That's all you have to do. But I digress. Getting back to the integration notation, we have that you will find that we have this symbol. That symbol is called an integral sign. An integral sign. This was introduced by Leibniz whenever he was working with these equations, trying to figure all this stuff out. And it's exactly what it looks like. It's an elongated S for summation instead of using the Greek letter sigma, because it's essentially saying the same thing, but it's doing it calculus wise instead of algebraic, and it's much easier once you get in there and you can really know the rules and everything. Unfortunately, starting this out to learn how to integrate, we're going to be working with definite integrals. That's not the unfortunate part. Definite integrals are great because they're super, I guess you could say easy, but they aren't easy. They're lesser of two evils, but I really like integration. But summation is a heck of a lot harder, which is unfortunately how we have to learn how to do the integral. And it'll make sense as to why, because it allows us to more intimately visualize what we're actually doing. But moving on, because we're going from left to right as we learn how to learn how to denote our stuff. So we have the integral sign. Next up is our limits of integration. So we have our limits of integration. And that's A for being the lower bound, and B for being the upper bound. And essentially, this is what signifies that we're doing a definite integral. It's these 2 points right here, that and that. That shows that we're doing a definite integral because it gives a point that we're integrating from to a point we're integrating to. And these two things are not interchangeable. This is your minimum, and that is your maximum, always. If you switch them, which it's possible to switch them, you're gonna get weird stuff going on. You're gonna pick up negatives and drop numbers and stuff like that. It's just easier to make sure that it's always your minimum. Sometimes a problem is gonna give it to you in a way that's switched to make your life harder, but we'll get to ways to get around that once we're farther into this. So for right now, A is always your minimum, B is always your maximum, right? Next is the easiest part, is our function that we're integrating, right? That's our function that we're integrating. And then we have the final piece, our dx. And that's actually probably the most important part of this entire thing. Now let's look at what this all means, because it's easy to just sort of see this and say, all right, slap some numbers on there and show me how to do it. But if we really want to get stuck in and we really want to know what we're taking the integral of, because this is how integration and derivation is how our modern formulas for knowing how the world works and knowing how science works and everything, that all comes from differentiation and integration. It's knowing how to do these things skillfully and what they mean conceptually that puts a good scientist above and beyond just a scientist. It's being able to look at a wall full of tools and grab the tools off of it. So if you're looking at the formulas and you know what the formulas are, you got a good set of tools that are pretty to look at. But if you really understand these core things and really know what each of them means, that means you could take those tools off the wall and use them. And that means you could do some pretty cool stuff. Now, another guy, he's just got a cool tool set, but you're out there making benches and things like that. So let's look at how we could take this off of our wall and really look at what this means. So let's say I had an XY plane. Nothing crazy, just an XY plane. And we had a function running through this plane like that. And it goes off in that direction indefinitely. Put our label our axes real quick. We had this function and we wanted to know what the value, if we were to add up this function, what that would be. Well, you may be asking, why would we actually want to do that? That doesn't make very much sense. Well, if we were to look at this conceptually, we were to say, okay, let's look at the area. Let's look at the area under this curve, because that's really what we're looking at here. And this is gonna say, we're gonna say that this is 1. That's 0. So we're looking from the x value of 0 to the x value of 1. What if I wanted to know what the area under this curve was? Well, we would take the integral. But first, there's got to be a way to sort of see what we're talking about here, right? Well, let's set up this integral as we're exploring what this graph looks like, okay? So we have our integrand, our integral symbol, I'm sorry, integral. We've already established what bounds we're doing this from. We're doing this from 0, from the x value of 0 to 1. And the reason we're not doing it in terms of y is because when you have that f of x in there, when you have this f of x in here, that's going to yield you a y value. So you can't evaluate from one point to another of a function that's going to give you those values. You have to do it from a second variable. So let's look at from our x. We have our 0 and we have our 1 because our 1 is our max, remember? Max and our min. Okay, well, let's just say this is some function f of x. Some of you who are graph experts will automatically know what function this is, but that's not necessarily important right now. It's more of the concept behind it. And then the last part, that d of x, right? Let's look at this and really understand what we're doing. Whenever we say d of x, we're talking in something that's rooted in an algebraic expression of a summation. And I just said a whole lot of long words there and confused myself almost, but what I'm saying is if we were to sum up this thing, if we were to let's make this a quantity. Let's say from a to b of f of x dx is equal to the limit. This is actually the first step in learning how to solve integrals. As n approaches infinity of sum from I equals 1 to n of f of x sub I, another continuous stream, delta x. Now, this, for right now, we're going to say that this dx and that delta x are actually the same thing, essentially. They're noting the same thing. Now, what I've written out here is the equation for, and we can actually, I'm sorry, I'm going to get rid of that. That's for the midpoint, but we can look at this and we can say, okay, well, this is the equation that we would use to solve this definite integral, right? We would notice our integral, and then we would set up this sum for our definite integral. And we're actually going to do this in that second video that I had mentioned earlier. It is just, as you can see from how long the explanation has been so far, um, it's it's definitely necessary to do these two videos. Um, let's talk about this. We're taking the limit as n approaches infinity, and n is some term across the entire function that we have over there, because this is going to be a function, and x sub I is essentially saying any any ith, any ith term. Now the ith term is any point x along this graph. So if we come back over here and we look at our graph and we say, okay, we have our y and our x and everything. If we look at here, that's x sub I, 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 that's x sub I. And we just take all these points. Any point on the x-axis for our function is x sub I. And dx is simply the distance between them. Or delta x is the distance between them. And that essentially is saying, all right, well, our dx, or our delta x even, is going to be extremely small. So we're going to be taking super small slivers as we go across here. So if the dx is the distance between them, I'm sorry, I keep saying dx, if our delta x is the distance between them, right there, it would essentially be effective, or more effective, to say, if, okay, at any time we take a singular point on this, any singular point, and just add all those up, those singular points we can label as dx. So if we pick up a little dx right there, right? All these values, dx, 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 all of them, that's saying the same thing. That is what our notation for our dx is coming from. So we take individual, single, very, very, very small slivers all throughout this function, and we eventually get that whole exact same line, right? That's safe to assume. If we add up individual points that are infinitesimally far apart, we will get this exact same line. Eventually, that green is going to just keep going and keep going and keep going until it covers up completely and matches exactly this original function. That's where our dx is coming from. So we get our dx. That is conceptually what an integral is. It's adding up, summing all the individual points across this, all these infinitesimally small points across a singular continuous function from a point A to a point B, adding them up, and then that will yield us the area underneath this curve. And in the next video, we're going to look at this formula right here and sort of learn how we can use this, or what we can do even to solve for it. And I would recommend for that having sort of a table, an appendix almost, of different things for whenever we sum up different sorts of i's in order to understand the examples. Most textbooks will have them. You can find it on the internet almost immediately, I'm sure, with a simple Google search. But that's going to be something that we're looking at in the next video. And actually, I'm going to go ahead and write out the formula that we're going to be integrating. We're going to integrate from 0 to 3. We're going to integrate from 0 to 3 x cubed minus 6x dx. All right? And we'll do that in the next video. And everybody, have a good day.